Hi, so let's go into video 2 then. So last time we did the kind of basics, a simple function to differentiate. Now getting a bit more tricky. So we're thinking now very much about what is differentiation, what we doing it for. That was before very much the process. Okay, so how we get from a function to a differentiated function. But what is differentiation all about? So before we get into this question, just have a little think with me. Differentiation about the rate of change. Now, what does that actually really mean? Okay, so if I've got a function, say this is my quadratic. Let's draw something like this. Yeah, we are thinking about the gradient of this function. Okay, so the gradient along here, I've got negative gradients, don't I? Because we know a line that goes this way has got a negative gradient, and a line that goes this way is a positive gradient. A line that's just flat has no gradient. So I've got negative, negative, negative. I've got no gradient at the turning point, and then positive, 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 positive. So the differential will tell me what the gradient of the line is. So if I was to, for example, draw this out, draw out the differential gradient, base. Say I've got so say this is x, and this is we come to this later on, but say this is x and y. I'd be saying, okay, well at 0, I've got my stationary point, don't I? So at 0 here, I have no gradient. Now this is my line of dy by dx. So say this is saying dy by dx is 5, 4, 3, 2, 1, all the way down to 0, and then -1, -2, -3. So I know at 0, right, at this point here, I know I've got 0 gradient. And I know before this point, I've got negative gradients, and after it, I've got positive gradients. So I'm going to have a graph, a differential graph that looks something like that. Because this line here is going to return negative gradients, and this part of the line is going to return positive gradients. You also notice that we've gone from a power of 2 parabola to a power of 1 straight line. Because each time you come down the powers, if we differentiate from x squared, we end up with 2x. So I've gone from a parabola to a straight line, and that's why you visually see that. So think about that when we're doing these questions. Okay, the rate of change, the differential is all about the slope of the curve. Okay. So let's start. So express in the form A. So this is great. This is tying in with your what's it called? Completing the square. I've got 3x squared plus 24x plus 15. I want you to write that in a complete the square. Okay, so I'll say take out my common factor of 3. So square plus, so I mean 8, 16, 24 plus 50. Very good. And then I'll say, right, I need to half my middle term, so 3 stays the same, and it's x plus 4 squared. So what I've done here is I've halved this middle term, and I get x plus 4 squared. And the general rule is that the 50 stays where it is, but what I need to do is take away the thing I've generated in this bracket. So this bracket here, if I was to break it out, and obviously you usually do this, but I'll just show you. If I was to break that bracket out, I've got x squared, I've got negative 4x, negative 4x, and 8. So x squared, I want an x squared, that's fantastic. I'll do this in a different colour, just so you see. So that's fine. I've got negative 8x. Sorry, I don't know why that's a positive. Sorry, that's my positive. I want positive 8x. There we go. So I've got positive 8x and I've got positive 8x. So I've got that. That's fantastic. However, just I've also made 8. I do not want this 8 in the bracket. When I write it like this, I've turned this into a function that's got an 8, which I don't want. And that's why we take away sorry, two mistakes. Sorry, two mistakes. It's not 8, that is 16, of course. Oh, I really should just restart this video, but I can't bother to apologise. I've generated a 16 that I don't want, so I need to take away the 4 squared to 16, but also that 4 squared is going to be times by 3. So you always want to take away this bit multiplied by this bit. I'm going to take away 4 squared multiplied by 3. So what's that? 4 squared, 16 multiplied by 3, 6, 12, 18, 48, 50 take away 48. Obviously because I was speaking and chatting, I'm unable to multitask. And that's me now completed the square. Fantastic. So that's a nice little 3 marks. And then it says find if f dash x, okay? So we're thinking that's quite good, that's bad, I'll do f dash x, so f dash x is going to be equal to 3x squared plus 24x plus 50. Excellent, okay, so given that, that's quite a nice wee 2 marks, isn't it? There we go, easiest 2 marks you'll get in the paper there. And then it says hence or otherwise explain why the curve is increasing. Now this is asking us, when it says hence or otherwise, it's kind of saying, well, look at what we've just done. So we have shown that the differential of this function is this. And we've shown you can rewrite that like this. So what we've actually done there is the question is trying to get us to think about and visualize the curve. Okay, so if I was to look at this curve here, where is my turning point? Well, the turning point is change the sign, stays the same. So -4 plus 2, so it's over there. And it's a positive x squared, so it's going to be a happy face. Okay, so this is my differentiated function. If this is dy by dx, this is x, and this is f dashed x, that is what this function looks like. That's why we do complete the square to get the turning point. Let's say, well, hence I always explain why it's always increasing. Well, it's always increasing because if you were to take any value of x, if I said x is -5, whatever it is, let's go over here, I'm going to return a positive value. If at -4, I will return positive value all the way to its lowest value, positive, and keep going and going and going. So you're always going to return a positive value because its turning point is above the x-axis. So how do we say that for the SQE? How does the SQE want that to be written? Well, they want you to say something along the lines of, well, x plus 4 squared is always going to be greater than or equal to 0, mate. Always, always. If I square that, it's always going to be greater than 0. So I know that this is always above the x-axis, okay? And that's for all values of x. A little bit of maths jargon there. All values of x. So if this bit's always greater than 0, okay, then obviously, goes without saying, if I times it by 3, if I'm multiplying that number by 3 and I'm adding 2, that is always going to be greater than 0 for all values of x. Therefore, it's always strictly increasing. I'm not sure if you would get the mark for drawing it out and stating that it's always increasing, because this is the mathematical way of describing that. Okay, but it's nice that you should be able to visualize that and say, well, yeah, that makes sense to me. I'm always going to get a positive value. So, but if you're wanting to write it for the SQA for your exam, this term is always going to be positive because any number squared will be a positive number. If I then take that positive and times it by 3 and add 2, I'm definitely always going to have a positive number. Okay, nice one. So that was almost a full video in just one question because I had a little preamble, didn't I? Now let's see if we can quickly get this one done. Find the x-coordinates of the stationary points. So let's just do this quickly. What it's saying is differentiate it. So it's going to give me a half times 4, which is 2. Take away 6x squared. So that's my differential. The stationary points occur when the gradient is equal to 0. And actually, I think we should probably write that, to be honest. We should say stationary points or turning points occur when dy by dx is equal to 0. And we talked about that at the beginning of the video, didn't we? So then I'm saying, okay, the differential is 0, and that's equal to 2x cubed, take away 6x squared. So now we have to factorize. So 0 is going to be equal to 2x squared, and that will give me x take away 3. So I know the x coordinates are going to be 0 and 3. Those values of x, I'm definitely going to have a stationary point. If I wanted to know the full coordinate, I would then substitute it back into the y equals a half x to the 4, take away 2x squared. I'd substitute these values in here to get the y value. So the big lesson from this one is knowing that your stationary points are when your gradient is equal to 0. So if you've got your any kind of function, some kind of that's actually a terrible. I don't know why I decided to draw that one. That's rubbish. You've got something a bit more obvious like that. Your stationary points here, turning point, stationary point. You see that the gradient of that is 0. Here you've got a positive gradient. There you've got 0. Then you've got a negative gradient, 0, and then positive. So watch out for that. That's a favorite question. So words like stationary points should resonate, differentiate. And I think we'll have to stop there, and we'll finish off with this question on the next video. I think this is one that was wrong in that bit. Okay, so see you on the next video.